Welcome to the second video in this linear algebra series. In this video, we're going to be looking at properties of matrix operations. So this video is going to be entirely proofs, and it is one of many videos that will be proof dominant within this series. We begin by examining the properties of matrix addition. So let A, B, and C be M by N matrices. The first property is A plus B is equal to B plus A. So matrix addition is commutative. Second property, A plus B plus C is equal to A plus B plus C. So matrix addition is also associative. There is a unique M by N matrix O such that A plus O is equal to A for any M by N matrix A. This matrix O is known as the M by N zero matrix. And finally, the fourth property, for each M by N matrix A, there is a unique M by N matrix D such that A plus D is equal to O. What we do is we write this matrix D as negative A, and we call it the negative of A. Now, what we're going to do in this video is only prove properties 1 and 3. The other two proofs will be left as an exercise, and I do encourage you to challenge yourself and try to prove them. So first, proving property 1. We're going to say A is represented like that. Remember, we looked at that in the last video. And we're going to represent B as this. And of course, they are both M by N matrices. Then from the definition of matrix addition, A plus B would be Aij plus Bij. Right, now this equals, what we can do is rewrite this as Bij plus Aij, and this is because each Aij, Bij are real numbers. And we know that addition of real numbers is commutative. But this is, by definition, matrix B plus matrix A, and so that completes the proof of the first property. Now proving the third property. I'm going to say let O be represented as Oij. Then A plus O would equal A if and only if Aij plus Oij is equal to Aij for all I and j. However, this holds if and only if Oij is equal to 0 for all ij. Right? Again, Aij is a real number. So the additive identity for real numbers is 0. This means that every entry of Oij is 0. So O is the M by N matrix whose entries are all 0. And so that completes the proof of the third property of matrix addition. We next look at properties of scalar multiplication. So R and S, let them be real numbers, and let A and B be matrices of the appropriate sizes. Then R times SA is equal to RS times A. What this is saying is if you're taking the scalar multiple of a scalar multiple of a matrix, you can just multiply the two scalars together first and then multiply that by the matrix. Second property, R plus S all times A is equal to R times A plus S times A. This says that scalar multiplication of a matrix distributes across real number addition. Third property, R times A plus B is equal to R times A plus R times B. Right? So what this one is saying is that scalar multiplication also distributes across matrix addition. And the fourth property, A times RB is equal to RAB, which is equal to RA times B. So if you're taking a matrix product and one of those matrices is a scalar multiple, right? It's a scalar multiplication matrix, then it doesn't matter where you move the scalar, right? So the easiest thing to do is to always convert it to this middle one, right? Take the matrix product first, then multiply that by the scalar. But this property says it doesn't matter how you do the scalar multiplication. Now, the proof of these four properties will be left as an exercise. So again, I encourage you to challenge yourself and try to prove these on your own. Let's now look at properties of matrix multiplication. First one, if A, B, and C are matrices of the appropriate sizes, then A times BC is equal to AB times C. So this is saying that matrix multiplication is associative. If A, B, and C are matrices of the appropriate sizes, then A plus B times C is equal to A times C plus B times C. Property 3 says that C times A plus B is equal to C times A plus C times B. 2 and 3 together state that matrix multiplication distributes across matrix addition. Now, remember, the order here matters. Where you write the matrix matters, whether you write it behind or in front. Notice there's no property for matrix multiplication being commutative. That is, A times B does not necessarily equal B times A. So the order in which you multiply your matrices matters. And that is why we need two properties. One where the C is behind the matrix addition, one where the C is in front of the matrix addition. We're only going to prove the first property here. All right, so we're going to have to define several matrices first. So let's say first A is of size m by n, B is of size n by p, and C is of size p by q. Now what we're going to do is define the matrix A as Aij, B as Bij, C as Cij. We're going to say that A times B is equal to a matrix D, and that'll be Dij. We'll say that B times C is a matrix E. We'll call that Eij. Say that A times B, then times C, we'll call that matrix F. That looks like Fjj, or Fij. And finally, A times B times C, we're going to call that matrix G, and represent that as Gij. We want to show that Fij is equal to Gij for all I and j. Right? So we want to show that the corresponding entries of matrix F and matrix G are the same. To do this, start with Fij. By definition of matrix multiplication, this is the sum, k equals 1 to p, of dik times c kj, right? Because remember, F is A times B times C. We said AB is D, and then obviously C. But D was A times B, so dik is also a sum. This will be the sum, let's say R equals 1 to N, and it's A times B, right? So it's A IR times B RJ. And then that sum is going to be multiplied by that CKJ. Now, what we're going to do is we're going to take this sum and write it in its expanded form. Okay? Right, so that is I1. I'm sorry, this should not have been BRJ, it should have been BRK. Right, so AI1 times B1K plus AI2 times B2K plus yada yada yada, so on and so forth, plus AIN times BNK, and then this is times CKJ. Now we can distribute the CKJ in through the addition. So we now have the sum, k equals 1 to p, of AI1, B1K, CKJ, plus AI2, B2K, CKJ, plus so on and so forth, plus AIN, plus B and K, I'm sorry, not plus, times B and K times CKJ. Now remember, summation is linear. Right? We studied that in Calc 2. So we can pull out constants and then split this sum into, or split the sum across all of the sums. Notice the index of summation is k, and none of the a's have k's in them, right? So we can factor out the a's. What we're going to be left with is this. We're going to have AI1 times the summation k equals 1 to p of B1K CKJ plus AI2 times the summation k equals 1 to p of b2k c k j, so on and so forth. And our final term would be ain times the sum k equals 1 to p of bnk c k j. But we can write this now as a sum, right? 1, 1 plus 2, 2, right? Plus so on and so forth, plus n, n. So this is itself a sum. So we can use summation notation to write the sum. R equals 1 to n of a I r times the sum k equals 1 to p b r k c k r, or k j rather. But this is exactly the ij entry of G. That is exactly what we wanted to show. And so this proof is completed. Again, the other two proofs are left as an exercise, and I do encourage you to challenge yourself and try to prove these. Finally, let's go ahead and look at properties of the transpose. All right, so we're saying that R is a scalar, and A and B are matrices of the appropriate sizes. Then we have four properties. A transpose transpose is equal to A. So if you take the transpose of the transpose, you get back to the original matrix. A plus B transpose is A transpose plus B transpose. So if you take the transpose of a sum, it's the sum of the transposes. A times B transpose is B transpose times A transpose. So if you're taking the transpose of a product, what we're going to do is we're going to reverse the order of the product and take the transpose of each matrix. Then RA transpose is just R times A transpose. All right, that makes sense because transpose of a scalar doesn't exist. And it's just the scalar itself, I should say. All right. We are only going to prove in this video the third property. Okay. The remaining three, again, will be left as an exercise, and you should challenge yourselves and try to prove them on your own. All right, so we say, represent A as Aij, B as Bij. We're also, as we did in the previous proof, going to define A times B as a matrix C. What we want to do is we want to show that Cij transpose is the Ij entry in B transpose times A transpose. All right, so start with Cij transpose. Remember, when you take the transpose, all you do is flip the rows and columns. So Cij transpose is simply Cji. By definition of matrix multiplication, this is the sum from k equals 1 to n of Ajk times Bki. But this is the sum of A kj transpose times B ik transpose. And since those are real numbers, multiplication commutes. So we can rewrite that as BIK transpose times A KJ transpose. Right? However, this is the IJ entry of B transpose A transpose, again, by definition of matrix multiplication. So that is what we wanted to show, and this proof is now complete. And with that, the second video in the series is now concluded. In the next video, we are going to look at special types of matrices, as well as some of their properties. Right, so there are going to be proofs again in the next video, but it will not be as proof heavy as this video was. Until then, I hope you all enjoyed, and I will see you in the next video.